students, today we will discuss applications of Euclid division lemma. So applications, we can explain the properties of the numbers using Euclid division lemma, like show that every positive even integer is of the form 2q and every positive odd integer is of the form 2q plus 1, where q is some integer. We will explain this property of positive and even positive odd integer and positive even integer using Euclid division lemma. So let a be a positive integer. Here b is equal to 2 if we compare this with 2. So b is equal to 2, then by Euclid's division lemma, a is equal to 2q plus r, where 0 less than equal to r less than 2. We are taking 2 in place of b because here b is equal to 2. So from this condition we can find out the possible values of r for remainder. So r is less than 2 but r is greater than or equal to 0. So therefore possible values of r equal to 0 and 1. These two values of r are coming from this condition, 0 less than equal to r less than equal to less than 2. So first case, when r is equal to 0. When r is equal to 0, then a is equal to 2q plus 0 is equal to 2q. So here we have a factor 2 and q is some integer. So this is form of positive even integer. This is the general form of positive even integer. Let us take second case, when r is equal to 1. When r is equal to 1, putting in this equation a is equal to 2q plus 1. So if 2q is even positive integer, then just next integer will be odd. Just like if 2 is positive, then 2 plus 1 equal to 3 is odd. So this 2q plus 1 is positive odd integer. So general positive even integer is of the form 2q and general positive odd integer is of the form 2q plus 1. So these are just like formulae for positive even integer and positive odd integer. Now show that any positive every positive integer is of the form 3q, 3q, 3q plus 1 or 3q plus 2 application we saw the positive, even and odd integer. In this application we are seeing only positive integer. We are not considering even or odd or general positive integer. So let A be an positive integer. Here if we compare, then this b is equal to 3. If we compare these three forms, then b comes out to be 3. Then by Euclid's division lemma, a is equal to 3u plus r, where 0 less than equal to r less than 3. We are writing 3 in place of b because b here divisor is 3. So from this condition we will find the possible values of r. R is greater than equal to 0 but less than 3. So therefore possible values of r come out to be 0, 1 and 2. These three possible values of remainder are given by this condition of the Euclid division lemma. So now we will take first case 1, when r is equal to 0. We will put r is equal to 0 in this equation, then a is equal to 3u plus 0 or it is equal to 3. So this is a positive integer in the first positive integer in the number. Now take for example when r is equal to 1. We will take value of remainder equal to 1 and put in this equation. So a is equal to 3q plus 1. So this is the first positive integer is of the form 3q, and next is next comes by adding 1 to it, so it becomes 3q plus 1. So this is also a positive integer. Case 3, when r is equal to 2, we will put value of r equal to 2 in this equation, then a comes out to be 3q plus 2. So here any positive integer is of the form 3q plus 1 or 3q plus 2. So any positive integer, it can be taken of the form 3q plus 1 or 3q plus 2, where q is some integer. Now let us take now we will discuss the questions of first exercise 1.1. Question number 2. So this is also application of the Euclid division lemma. Show that any positive odd integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5, where q is some integer. Here also we will apply Euclid division lemma. Let A be any positive integer. If we compare this with the Euclid division form equation, then b comes out to be, here b is equal to 6. Then by Euclid's division lemma, a is equal to 6q plus r, where 0 less than equal to r less than 6. So here we are taking 6 in place of divisor b by comparing with these three forms of the positive odd integer. So from this condition of Euclid division lemma, we will get different possible values of r. So from this condition, the possible values of r come out to be 0, 1, 2, 3, 4 and 5, because remainder is greater than equal to 0 but less than 6. So these 6 values come out to be possible values of the remainder. Now we will take one by one these possible values. Case 1, when r is equal to 0. We will put r equal to 0 in this equation. So a comes out to be 6q plus 0 or 6q or 2 into 3q. So this is the positive even integer. So 6q is the first form of the positive integer. Now let us take second case, when r is equal to 1. We will put r equal to 1 in this equation. So a comes out to be 6q plus 1. Now if 6q is positive integer, then just next integer will be odd integer. So this is the odd positive integer. Now let us take third case, when r is equal to 2. R equal to 2. So a comes out to be 6q plus 2. So if 6q plus 1 is odd positive integer, then just next will be even integer, and it can be shown as 2 into 3q plus 1. So it is positive even integer. Now let us take next possible value of r when r is equal to 3. Now we will put r equal to 3 in this equation. So a comes out to be 6q plus 3. If 6q plus 2 is a positive even integer, then just next will be its odd negative integer, odd positive integer. Now next possible value of r is case 5, when r is equal to 4. Now we will put this r equal to 4 value in this equation. So a comes out to be 6q plus 4. So if 6q plus 3 is all positive odd integer, just next will be positive even integer. This can be shown by taking 2 factor common, 3q plus 2. So this is positive even integer. So next possible value case 5, next possible value is when r equal to 5. So putting this r equal to 5 in this equation, 6q plus 5. If 6q plus 4 is even positive even integer, then just next will be positive odd integer. So in this question we have shown that 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5, they are positive odd integer in this example. Now let us take next question of this exercise, which is also application of the Euclid division lemma, one of the applications. In an army contingent, there are 616 members, and they are to march behind the 32 members in the parade. These two groups are to march in same number of columns. What is maximum number of columns in which they can march? So total members, question number 3. Total members equal to 616, and members of band party is equal to 32. So these 616 members of the troop, they are to march behind these 32 members. So this can be found out by find out the HCF of 616 and 30. So number of columns found can be found out by finding HCF of 616 and 30. So HCF we can find out by dividing next. It will so this first division fact can be written as 616 is equal to 32 into 19 plus 8, and second step can be written as 32 is equal to 8 into 4 plus 0. So this last divisor is the HCF of 616 and 30. So total number of columns will be equal to 8. So this is one of applications of Euclid division lemma. This is how you can solve the problems, and this is all for today. Thank you.